Okay, so welcome back. Let's look at chapter 6, monad transformers. And I think this we're going to need when we want to combine different monads into like one monad. Like if you, for example, want a state monad and also want exceptions. Yeah, so in the previous chapter we saw already that a monad is a way to encode side effects in a pure language. And it's not even just limited to stuff like I/O or exceptions that other programming languages have. You can also encode stuff that other programming languages don't have, like non-deterministic searches or continuations. And typically, if you write an application, you're going to have like a functional core, like easily testable functions that are just written in a purely like functional style, usually even like without monads, for example. And then you have like an imperative shell that uses like monads, for example, to interact with the outside world. And in the previous chapter we saw several examples like encoding mutable state, encoding error handling, or stuff like logging. And writing all these by hand, especially if you have a monad that needs like multiple side effects, can be quite tedious. So instead what we're gonna do is write a definition that modifies some other monad to add an additional effect, and such a definition is then called a monad transformer. And then we can build a concrete monad by combining several monad transformers. 6.1 Combining I/O and reader. So in the previous chapter we already saw the reader monad, and one use case for that is when you want to pass like a configuration or a context that's needed by a lot of functions, but you maybe don't want to pass it as an explicit argument all the time. And the example we're going to build here is like a tree program that prints a directory tree, and it's going to have the option of using either Unicode box drawing characters or ASCII characters. So if I just, for example, this is what the normal tree command looks like, right? Draws this nice tree with Unicode line drawing characters. And if we pass charset equals ASCII to tree, then it's going to use the normal ASCII characters to draw the lines instead of the nice Unicode characters. And they're creating an example directory structure here to test the program. And their version of tree is called doe. And you can see it's printing it like that. Actually, in the normal like tree, it wouldn't print these lines here because they're kind of useless. You can see here that there's no line going down to the bottom. 6.1.1 Implementation. Yeah, we're going to create a configuration structure that has use ASCII as a boolean and the current prefix. Yeah, by default we're going to use Unicode with no prefix. And then we make a function to print the usage information. Okay, we're making a function to construct the configuration from command line arguments, so we get a list of strings and return a config. If the list is empty, we just return the default config, and if it is -- ASCII, we set use ASCII to true, and otherwise we like return none, so otherwise it's an invalid argument. Yeah, so can test that it works. Appears to be working. Okay, let's see what the main function does. First, it's going to process the arguments and print an error in case that the arguments are wrong. Otherwise, we're calling this dir tree function with the parsed config and the current directory. Okay, so in order to use my definition from doc.lean, I had to put this here, import chapter6.doc into the like root of the module. Yeah, and we're seeing here that they're using this eprintln, which is just like println but outputs the standard error. And we also need to keep in mind that we need to skip the files named dot and dot dot, as these aren't actually files, but they're just like virtual like links that the operating system generates. They're not like physically there. And of the files that we do show, there's two types, either normal files or directories. And we're going to define this toEntry function that takes a file path and returns an optional entry, or rather returns a like IO action that will yield an optional entry. Okay, first of all, appears to work correctly. If we test it, let's see. And so this path.components function just seems to essentially split at the slashes, even with like an empty string at the beginning. And if there's no last component, we're just going to return a directory with the empty string, and the syntax here like infers the namespace, I guess, based on the type. So we could also spell this as entry.dir, obviously. Going to ignore the dot and dot directories, and otherwise we're going to just check if it's a directory or not, and then use the appropriate constructor. Yeah, so this first case here is like only going to be relevant in the root directory of the file system. This is actually a good point. So Lean doesn't know that directory trees are finite, and obviously they don't actually have to be. So they don't have to be trees at all. You can just create a circular structure, and that's why we need to declare dir tree as partial. Yeah, so I can, for example, create inside of A, I can create a link to itself, and then I can just go deeper and deeper, and they will always end up inside of the same folder, but the path will get longer and longer. And actually, if I do a non-symbolic link, so if I just do, then it actually gives me an error. And so, yeah, with a hard link, actually it doesn't work, but let's try creating a directory A and using a bind mount to like mount the parent directory there. Well, we get a little error, but does kind of actually seem to work. So let's try doing tree, and somehow tree is smart enough actually to not go into an infinite thing here. And Alice is also smart enough to not go into an infinite loop. Great, I thought I could maybe get some of these tools to like loop infinitely, but apparently not. What if we try the symbolic link case again? Well, still smart enough. If we pass dash dereference that it dereferences the link, it's still smart enough to detect that it already listed that. Okay, so let's look at the dir tree function. I guess first we're going to write it with taking the config explicitly, then also takes a path and returns an IO action. First we're checking the entry of the path. We return a no op in the none case. Then we have some logic to show a file name in the file case, and for a directory case, obviously we need to recurse. So we're going to show the name of the directory, get the contents, make up a new config, and then we're going to sort the contents of the directory, and for each of them, I guess, call ourselves recursively. Yeah, we can also see that for the nested action here, that the parentheses are optional in this case because it's unambiguous. Yeah, next we're going to define this dir less than function that we use to compare directories, and we're just comparing based off the name here. And then we're going to define these functions to render file names and directory names, and I guess we're just going to use a function that we're going to define later and then just print the result. Yeah. I think here we again see some kind of curious thing with Lean, is that it doesn't allow you to use definitions even if they're in scope. You have to actually define it before it's used somehow, like in C, for example. But most languages, I think these days, have no problem if you use something if that's defined later in the same file. Yeah, we have two versions here. For files and for directories, and they take into account whether to use ASCII or not. And then to render it, we're going to use string interpolation to print the current prefix, the pre-file prefix, and then the file itself. And for directories, we're going to print a slash at the end, otherwise it's identical. And config.in directory is going to extend the prefix with a directory marker. Yeah, so essentially we are modifying the config that we are passed by adding something to the current prefix. And since this is defined in the config namespace and takes config as the first argument, we can call it using this dot notation. Yeah, if it was not in a config namespace, it's not actually going to resolve that. And we're defining this toList helper here, which we define for applicative because we don't actually need the full power of the monad abstraction. And it's going to take a list of alphas, a function that essentially turns these alphas into actions. So our f is, our applicative here, but in general our monad. And it's going to combine them into a single action, I guess, or a single side effect. And this is using the seek write operator, which takes like an action that produces alphas, I guess, and like a deferred action that produces beta. So again, I think this like function from unit to f of beta here again is to like simulate basically the laziness that we can evaluate it inside of our function and it's not evaluated before the function itself is called. And yeah, we're just going to throw away the alpha and return the f of beta result. 6.1.2 using a custom monad. Yeah, and the way we've implemented it now should actually work fine, but it's kind of error prone to have to pass around the configuration all the time. And we can use a reader effect to automatically pass the configuration and make it less verbose. And actually, before we check that out, I think we should try if it works at all. And yeah, it does appear to work, though, as we noted earlier. Like, it's not a very nice tree because it prints this useless line here that doesn't lead to anything. And also to actually be useful, it should, I guess, ignore hidden directories like the git directory. Okay, so we're defining this function config.io, which takes a type alpha and returns another type. And I guess the type it returns is the type of functions from config to io of alpha. And then we're defining a monad instance for config.io, where pure is just defined to be a function that ignores its argument. So I guess ignores the config and just calls... this looks like it calls itself recursively here, but I think this is going to be then a different monad instance. Let's actually copy paste this. So the type of our outer pure is alpha to config to io of alpha. The inner pure is alpha to f of alpha. So I'm a bit confused right now, but I guess this is then going to be the pure of the io monad. Let's see how bind works. So we get a result and a next action, and we return a function that takes a configuration, where it computes the result by giving it the configuration, and then calls this next. So next has type alpha to config io of beta, and what we want is an io of beta. So we also need to give it two arguments, right? We need to give it the previously computed result and then also the config. And I wonder if I can rewrite this expression here without like the lambda expression. At least it doesn't give a type error, so now it looks even more confusing. Yeah. Yeah, and this is a good point here that the do notation we see here is obviously for the IO monad and not for the monad that we are defining right there. And the IO monad's bind operator is then going to ensure the order of operations so that all the side effects of result are performed before the side effects of next, right? And yeah, thankfully they didn't make config.io universe polymorphic because I think that would have only added to my confusion. Now we're going to define a run function for our config.io action. So we get our action, which remember is just like a function, right? That takes a config and gives us an IO action. And we actually get the config and we return the IO action, and obviously we do that by just like running the function. Yeah, that's really kind of a convention to do this. Obviously the caller could just like directly use this here. Like they don't save many characters by using config.io.run, but that makes it sort of clear which parts are intended to run in which monad. And to make our config.io actually useful, we need some way to access the config, which is why we define this current config helper, which will return a config.io action that results in a config. And obviously for config IO actions, the config is the first argument, so, or the only argument. But so this is just going to be a function that takes a config argument and then like wraps it into a monadic result. Yeah, and the pure that we are seeing here is the pure of IO. So in the reader monad, we just return the config directly, I think. But here, yeah, we have to call this pure to like wrap it into the inner monad, into the IO monad. And we also need a way to actually override the configuration. So we define this function locally, which takes a function that modifies the config and an action, and it returns another config IO action. And the way it's going to work is just we take our initial config and we run the action with the modified config. But obviously this is not going to like, for all subsequent actions, the config will not be changed. So I guess this is why it's called locally, because we're just changing it for that one action. Now, obviously, a lot of the time we just want to run regular IO actions that don't need the config. So for that, we define this helper run IO that will just ignore the config and just give us the IO action. So now we can update show file name and show dir name, and we're just going to like use the same code but wrap it into this run IO to make sure it executes inside of the IO monad. Okay, let's see how we can update our dir tree with this locally helper. I mean, obviously we need to update the type. And then our toEntry function just is run in the IO monad. And we read the directory and we locally modify the config using in directory. Let's see here. Which is using like this, we're using this shorthand like lambda expression syntax here. And honestly, I think in directory is a bit confusingly named, but basically just increases the nesting level by 1. And I guess our doList function was generic in the monad type or in the applicative type, so it's going to just as well work in our config IO monad. So in this part, I guess there's not really any changes. Let's see if it still works. Apparently not. Well, we haven't updated main yet. Yeah, so we can see that the difference here is that we are calling config io.run. So we call this directory with the current directory, and it gives us a config io action, and we run it by giving it our parsed config. And it in fact works the exact same way. Yes. Yeah, now we look at the advantages of our new approach. It's easier to ensure that the configuration is passed down unchanged and only changed when we actually want to change it and not accidentally, which honestly I don't really see a huge difference here actually, since I mean stuff in Lean is obviously immutable anyway, right? So it's hard to accidentally change stuff. From a software architecture point of view, we have now separated the concern of printing the directory contents from the concern of passing down the configuration. And I mean, if our program gets more complex and gets more intermediate layers, then these layers don't need to like be rewritten to like pass down the config. That will just happen automatically with the monad. Let's look at the downsides. If we evolve our program and we require more features, or I guess explicitly or specifically more side effects, then we will need to update our monad and we will need to define new helper functions like locally or current config. It was a bit annoying that we had to wrap all of our IO actions using run IO, so it just added like visual noise to the program. And it's repetitive to keep adding these monad instances for the side effects that we want. And we can address this by using monad transformers, which, like as the name kind of implies, are going to be taking a monad as an argument and returning a new monad. And they're going to consist of the definition of the transformer itself, which is a function from type to type, and a monad instance that assumes the inner type is already a monad. And then we will need an operator called lift to lift an action from the inner monad to the transformed monad. So in our example, that was run IO. 6.1.3, adding a reader to any monad. Yeah, so in the Lean standard library, there's this function called reader_t, which will allow us to add a reader effect to any type. So we have a type row in universe U. We have a function m, which goes from type universe U to type universe V. And we have a type alpha also in type universe U. And we're going to return a type in the maximum of those two universes. And the type is just going to be row to m of alpha. So in our example, row was the config, right? M was the IO monad, and alpha was also generic in our example. And alpha and row need to be in the same universe because the operator that retrieves the environment in the monad will have type M of row. I mean, I have to admit that this whole type universe business is going a bit over my head right now. But from the signature we can see that, I mean, row is in universe U, alpha is also in universe U. Yeah, and if we use reader_t, our config IO definition becomes, well, just this. We can just rewrite it using reader_t. And again, for technical reasons, we need to use abref instead of def here to make sure the definition is reducible. And essentially this will make sure that config IO behaves identically to just writing out reader_t config IO. And we had this helper function called current config to obtain the environment again. And in the reader_t case, it's just named read. So given a monad instance M, the type of read is reader_t row m row. So it takes a config of type row or like a environment and also returns the same environment again. And this read operator is not restricted to reader_t. There's a type class for it that will allow any monad to provide this read operator. And I think we need this out param gadget here to kind of delay the inference of this type row, maybe, I'm not sure, until after we know like the type of the monad itself. And we can also see that for some reason we need to add 1 to the universe here. Yeah, again, going a bit over my head why we need to do this here, but anyway. And then the type of read is going to be a monadic action that yields a row. And if we have a monad instance M, then we can define a monad reader instance for reader_t of row and M. That works like our current config helper we had above, so just returning the environment literally. And we're exporting the read function here so that we don't have to namespace it, a monad reader namespace, I guess. Yeah, and they're saying that we're using the out parameter because it's common that a monad only provides a single type of environment through a reader. So I guess the type of monad like uniquely determines the type of row, and somehow that will cause it to be automatically selected. Though honestly I saw that the automatically selected types are the ones that we put into curly braces, so I don't really know what the difference here is to using that out param. Very kind of, yeah, complex stuff it seems. And so here we're saying that if M has a monad instance, then reader_t of row and M will also be a monad, and we define the monad instance by, well, for pure ignoring the environment and delegating to the inner monad, and for the bind operator doing the work of actually passing the environment to well, the result computation and then also to the rest of the computation. And next we want to eliminate the explicit use of run.io. So when Lean encounters a mismatch in the monad types, it will automatically use this monad lift type class to attempt to run our action in the correct monad. Yeah, in a similar process to coercion. And the class monad lift is defined to be, well, generic over 2 type parameters. First we have a function on the type level m, which is going to be our monad type, and we have n, which I guess might be another monad type. And we can see that the type of argument that they take has to be like in the same universe. And we have this implicit parameter of alpha here. And then we're just going to go from one monad to the other monad. And it's called lifting because we're taking an action from the inner monad, so for example IO, and making it into an action of our surrounding monad, so for example config IO. So we also need to define an instance for that. So for any monad M and reader G of row and M, monad lift is just going to be done by ignoring the argument. And if we have that, then this is enough to define show file name and show dir name without using run IO. And we still have to transform our locally helper to the standard reader G version. And the standard version is called with reader, and it's also part of a type class. So given a type row and a monad, I guess, with reader is going to take a modifier function that goes from row to modify our environment, and a monadic action, and it's going to run that action with the modified environment. And we're also going to export it so that we don't need to like namespace it, or like that we don't need to specify the namespace when calling it. Yeah, the definition is going to be the same as our definition of locally. So we take a change and an action, and given the configuration, we apply the change and then we apply the action to the changed, or like with the changed config. And now we can write a new version of dir tree where we replace locally with the with reader function. So they admit that we didn't really save a lot of code with this, and but the advantage is that we're now using like a standard functionality, and someone who knows Lean is gonna read this code, they're gonna have an easier time understanding it since we're just using the standard reader monad. And if we imagine that we wanted to change our implementation, for example, to count the total number of files using a state t monad transformer, then this would be easy to add in our new version compared to the old version. So because we don't need to change all intermediate layers. And finally, using these like monad transformers, we can also make our code more generic. So we can write functions that work for any monad that provides a certain type of state or a certain type of exceptions without having to describe in the type how it provides the state or how it provides these exceptions. Exercises. So file names that begin with a dot should be usually hidden in a directory listing, so we should add an option to, I guess we should hide them by default and add an option to show them. So I guess first we need to modify the config to add like a show hidden. Then let's see, modify the usage. Thanks AI. And now I'm not sure what the best way to do this is, but I guess we need to have some sort of recursion here. So my intention here is to like, if the first thing in the list is --ASCII, then I want to like parse the rest of the list as a config and modify that config to set the use ASCII to true. And the same for show hidden, though somehow I'm not that happy with this structure. Like I think there should be probably some more elegant way to do it, but well, let's see if it works. So if I pass -a and --ASCII, then we will have both of those to true. And now I guess into entry we need to check some additional stuff. And actually, as far as I know, that Lean somehow has a way to like add control flow to monad. So actually return should work, I think, like as expected, like should like short circuit the monad. Let's try. Yeah, that seems to work correctly. So if I do .docs here, it gives me none. Yeah, that's actually I think one of the cool things about Lean. Like in Haskell, return is just an alias for pure actually. And the same actually for this do list helper here, which we wrote like to do like recursively go through the list and like apply this action. As far as I know, in Lean, inside of do notation, you should be able to just write a for loop. The question is, do I even need the extra do here or not? Apparently I do. Yeah, let's try it out. And yes, it does not show my .git directory anymore. If I do -a, it also doesn't show it. Great. I guess we forgot to actually check the condition. Okay, so I guess we need config IO here. Nah. Okay, now I rewrote it to be in config IO, which means I need to like run it, and I need to somehow, this now it's not giving me any error, so I guess with read we should get the config and then check show hidden, and it doesn't work, so show hidden is false, but we still get this, so I guess we need to invert it. Now if we set this to true, then it's there. If we set it to false, then it's not there. Okay, great. But somehow I'm getting an error because, yeah, I had this thing still going around here. Okay, let's restart. Okay, we can see our .git is listed, though I feel like we broke something else now, since this looks not how it's supposed to look. But right, let's remove this option now. Now it looks like this. Okay. Yeah, we're not even using the file name and dir name thing anymore. Okay. Yeah, I think that the version in the book here is just buggy. Should delete current config. Let's restart this. Better, but not good. Let's try just using prefile and predir, maybe without the spaces. Yeah, I broke something again. Yeah, here we also need prefile. Yeah, now it looks about right. Okay. And yeah, another thing we could do is take the starting directory as an argument. So let's add start dir and just as a string and set it to a period. And here I would really like to have like a guard here to say that this can start with anything but a minus. Can we do this? I mean, like something like this, right? But I guess this is not working. Yeah, cannot figure out if that's somehow possible. So I guess, yeah, I mean, if we like do it like this, then at least I guess it's going to not accept anything with a minus as a directory, but we can still like supply as many directories as we want. So, okay. Well, so I guess what I was trying to do here is like preventing you from like passing multiple start tiers, because then it would only use like the last one, or actually only the first one. But then I guess you still can like pass multiple times like the current tier and would just ignore it. Like let's try this. We have start tier is my tier, but if we pass another one, then we get none. But if we just pass another period, then yeah, it's just going to ignore it. So I mean, yeah, I'm not going to spend too much time like making this nice anyway. And here now we need to pass a config.startdir, maybe restart it, and this should convert it to a file path. Yeah, let's try. So if we pass nothing, somehow now it prints nothing. If we actually pass a start here, it does print something. If we just pass a period, because we are ignoring periods, so I guess we need to somehow, if possible, like return it to an, make it into an absolute path. which I cannot figure out. Also really funny that we can just have mutable variables in Lean inside of do notation, but well, since I cannot figure out how to convert it to an absolute path, and I don't want to add a special rule to print like the dot in the top level and ignore it in the other levels, I'm going to try with this, and yeah, now it works again. Okay. 6.2, a monad construction kit. So in this section we're gonna see some other monad transformers other than reader T, and each of them is going to consist of the following three things. So a data type T that takes a monad as an argument. So it's going to have like a type like taking a function from type U to type V as the first argument, and then taking a type U and then giving you a type V, and it may obviously accept additional arguments prior to the monad. So let's check this for reader T. We have one additional argument here, which is our type row. Then we have our monad from type U to type V, and we get our alpha, right, which is the type parameter of the monad, and we return a type of max UV. So not the V type V like here. Yeah, and then obviously our monad transformer is going to need a monad instance for Tm that relies on the monad instance of M. This enables us to actually use it as a monad. And then we also need a monad lift instance that can translate actions of type M of alpha to actions of type T of M of alpha. Yeah, so that we can use actions from the underlying monad in the transformed monad. Obviously we need to follow the monad laws, and we have some additional laws like monad lift of a pure value x in the monad M of alpha should be equivalent to pure of x in the transformed monad, and monad lift should distribute over bind. Let's see. If we do monad lift and we have x bind f inside of our M of alpha monad, that needs to be the same as monad lift. So we directly lift our... Okay, so I think the precedence here is that this is like one expression, right? So this expression here is of type M of alpha, and we bind that then to a function that takes the result and applies it and then lifts the whole result. So basically like lifting this whole bind operation here should be the same as just lifting the argument and lifting the result, if I read this correctly. And each monad transformer typically is going to have a type class like monad reader to describe the actual effects that are available. And this will make us even more flexible in like writing generic code, because if we use the monad reader type class, then we are not even limiting ourselves to monad instances defined using like the reader T transformer. We could obviously also implement that type class for anything else. Yeah, so the way to think of this is the type classes express our requirements, and the monad transformers are one convenient way to meet those requirements. 6.2.1 failure with option T. Yeah, so both the option and accept monad represent different types of failures, and they have their corresponding transformers. So for example, you could have IO of option of alpha to represent an IO action that doesn't always return a value of type alpha. So let's look at how we can define option T. So we get our monad, we get our type alpha, and we return a type V, so in the same universe as the original like parameterized monad type will be. And yeah, we're literally just wrapping alpha in an option. So using that, you can define a function that gets some input from the user but returns a failure if there is no input. So we call getLine on stdin. We trim the line. If the trimmed line is empty, we return failure, otherwise we return the trimmed string. So if we make this structure user info where we have a username and a favorite beetle. Then we can define a function getUserInfo that returns a monadic action in the option t IO monad. So we need to print what is your name, get the name, print what is your favorite species of beetle, then get the beetle, and obviously at any point here we can fail, and then we return the user info. Yes, obviously in this eval environment here we cannot get user input, but we can see it prints what's your name and then goes into the failure case because we didn't provide a name. Yeah, it's also written here, if the first case here fails, then control never reaches the second question. So if we define a function interact here by matching the user info, we can see that it's printing what's your name and then missing info. 6.2.1.1, the monad instance. Yeah, we will encounter some difficulties here. So based on the types, pure should just use pure from the underlying monad together with some, and bind should like propagate none, and otherwise like run the inner monad, I guess. And we see that both of those give us an error. So we have a type option alpha, but we are expected to just have an alpha. And the error is actually just that Lean is using the wrong instance of pure and bind. And one way we can solve this is by just adding type annotations. So we're saying that pure of sum of x is of type m of option of something, and that this branch here is also of type m of option of something. But that's kind of not really elegant. And the alternative is to just define a function to guide Lean to the correct instances. And I guess we're doing this by changing our definition of option t, by saying now it's defined as a structure that just has this one run function associated with it. But the downside of that would be that the resulting code would get more complicated, and yeah, that it can also make proofs more complicated to read. So what we're instead going to do is to define functions that serve the same role as we would have like in the structure, like the constructor and the accessor, but working with the direct definition. Actually, what is the direct definition? Yeah, just like this. And we can see that these are both like identity functions actually. Like they just change around the types. So from m of option of alpha to option t of m and alpha, and then in the other way around. But what they do effectively is indicate the boundary between code that should present us with the interface of option t and code that should present us with the interface of the underlying monad. So with this, our instance now becomes readable. We just call option t.make here and also here. And this indicates to Lean that the code inside of this call here, for example, to make, is using the inner monad m. Yeah, so we're going to prove here that the monad contract is satisfied. I'm not going to go through all of the steps, but we want to prove that bind of pure v and f is, well, just the same as f of v, which it turns out it is. And then we need to check that bind of w and pure is the same as w, which in the end will follow from the monad laws of m. And the final rule is then that bind of v to f to g is the same as binding v to a lambda expression that binds the like result of essentially running f of v to g, like f of x, but x is the unwrapped value of v. Yeah, and now even the author has given up on like expanding all the definitions, but I'm sure we could check that this is the case. 6.2.1.2, an alternative instance. Yeah, so we can use option t through the alternative type class. That's the one that provides this failure operation and this neat little operator to get the leftmost sum instance. So given a monad instance M, we can provide a alternative instance for option T of M, where our failure is just going to be pure none, and our or else operation, let's see, we're like running the first action here, and if we get some result, we just return it. No need to evaluate y, and if not, then we evaluate y. And again, we're using this pattern of a function that takes unit to like simulate the lazy evaluation. Essentially, that's why we're passing unit here. 6.2.1.3 lifting. Lifting is easy, so we just lift by wrapping it in sum. So let's see, given a monad instance M, we provide an instance of monad lift for M and option T of M, where monad lift, so I'm going to review the type of monad lift real quick. We want to go from M of alpha to option T of M of alpha. So we have this action, and I mean, essentially we just want to wrap it in sum, but this seems like an awfully verbose way to do it. Maybe it's again to do with the type system stuff that we call this option t.make and then use do notation inside of it. Let me see. What if we just like don't? Action is type M of alpha. Yeah, I guess for some reason if we like literally just take the action and do pure sum, then we need this sort of type annotation because it cannot figure out the correct type on its own. 6.2.2 exceptions. Yeah, it's going to be similar to our option transformer. So let's see, we have our except t, we take our exception type epsilon, take our monad, our type parameter for the monad, and the result is going to be another type, and the type is just the original monad containing a except with epsilon and alpha. Seems simple enough. We're going to do the same trick as before by like defining this pseudo constructor and run function that are both like identities that just do funny stuff with the types. And yeah, the monad instance is going to be essentially the same, except that we need to propagate the error value. And again, we're using our constructor here to guide the type checker on the right path. And in this instance here, we are explicitly annotating the universe, so we are forcing epsilon and our alpha, which is this part here, to be in the same universe, because otherwise Lean would write a more general instance where they are in different universes, which wouldn't work because we want to provide both of them as an argument to M. And honestly, I think this is the type of stuff, like if I was writing this instance and I like made this mistake, I would probably never be able to figure out what the error message was. Yeah, so we would get like stuck at solving universe constraint. Yeah, so if we define the except.mk without the explicit universe levels, like without forcing epsilon and alpha to be in the same universe, yeah, we get this. Yeah. The author admits here diagnosing this can be tricky. And so the difference between option and except is that option is kind of like both a control structure and a data structure, whereas except is really only used as a control structure. And that means that it's reasonable to just lift except of epsilon actions into except t of epsilon and m, as well as actions from the underlying monad m, where I'm not exactly sure what they're trying to say here. So if we lift except actions into except t actions, we can just use the pure of the inner monad, because the exceptions cannot affect the inner monad. Let's see, so we have our monad instance M, and we want to provide a monad lift that takes an except of epsilon action and gives us an except t of epsilon and m for our monad M, where we are just going to use pure. And if we want to lift from a monadic action in M to accept T, then we're just going to need to wrap it into the OK constructor. And we're using like functor.map here to do that. 6.2.2.1 type classes for exceptions. So in exception handling, what we want to do is throw exceptions and also recover from them. And obviously we could do this, or we can do this by pattern matching using the constructors of accept. And obviously this will tie our program to the specific encoding of the exception handling effect. But if we use type classes, then we can generalize this to be used in any monad that supports throwing and catching. Yeah, so throwing an exception should obviously take an exception as an argument, and it should be allowed in any context where we're expecting like a normal monadic value. So we're going from epsilon to m of alpha here. And try catch gives us, well, takes a monadic action and then a function that recovers essentially from the error. So we need to provide a way to, like, for example, give a default value in case of error, so that in the end we can get back to our m of alpha. So here we are not imposing the limitation that epsilon and alpha need to be on the same level. And apparently this is because we never place an exception value inside of M in monad accept. So epsilon and alpha are completely independent, and that will allow us to, well, use this type class in a wider variety of types. So we're going to make an example program that uses monad accept by just performing division, and we're going to structure it into a front end and a back end, both of which can throw exceptions. So we have our error type where one error is diff by 0 and one is not a number. So if a string is just not a number. So let's see the back end first. We have a monad M, we have a monad accept instance for our error type and M. Take two integers and we return, well, a monadic action that can give us an integer. So we can see if k is 0, we can throw divide by 0. Otherwise we can just return n divided by k. And the front end is going to just parse our strings to ints and then call the backend. So we need a function as number, which again has this m that's constrained to be a monad and have a monad accept instance for our custom error type. Takes a string and returns a monadic action that can give us an integer. And we call this s.toInt function. If it returns none, then we throw our not a number error, otherwise we just return the number. And in the front end, again, same constraints here. Now we take two strings and return the result also as a string in a monadic context. Then we have our try catch here, which has first this do block here where we are really making use of this inline notation where we're like parsing both numbers first and then calling our backend and then converting the result back to a string. And catching our error, we use this special notation here that is like a lambda with one argument and then matching on that argument. So we can like leave it unnamed and not use the match syntax explicitly, but like just implicitly writing these pipes. And obviously just we're going to print a helpful error message. And this is such a common thing that Lean decided to add a special syntax for it. So we can just write this as try and then catch. And notably that try seems to imply a do block, so I guess we don't have to write the do here. So apparently we can also use the try catch syntax with option, because there's a monad accept instance with unit and option. So obviously option contains no error data, so we can just use like unit as the error type. 6.2.3 state. So we can simulate mutable state by like passing the starting state and returning the final state. And obviously with monads we don't have to pass it explicitly. The bind operator can do this for us implicitly and like thread the state through the program. And yeah, now we can also do this with a monad transformer. So we have our sigma in type universe U. Then we have our, well, monad that's parameterized in a type in universe U and is going to result in a type of universe V. And we get our type parameter that's also in universe U, and we're going to give a type that's in the maximum of U and V. And the way it's going to work is just that this is like our monad actions are going to be functions that take a state and then return an action in the underlying monad that returns our like alpha, our result, along with the final state sigma. Yeah, this is very similar to the normal state monad, except that we are passing around the state inside of the underlying monad rather than with pure code. Okay, let's look at the monad instance. So given a monad M, or like a monad constructor M, I guess, we have an instance for monad for state T of sigma and M, where, well, pure is just a function that leaves the state unmodified, and bind, well, applies the result action and threads through the final state. And then we're also going to have a corresponding type class that has get and set methods. Well, obviously with mutable state, we always have to be careful that we don't set the wrong state. So now we have an example program to count the number of diacritic-free English vowels and consonants in a string of letters. So the result is going to be this letter count struct, which has vowels and consonants. We have this error type, which is not a letter. We define our vowels to be like the lowercase and the uppercase vowels, and same for the consonants. And now we define our count letters function, which takes a string and returns a state T with letter counts as the state and except of error as, I guess, the inner monad. And we are giving unit here because actually we don't care about the result of the computation, we only care about the side effect, which is this letter counts. So we have a recursive let. So we're going to call it with our string converted to a list. So we have a list of chars. We're going to match our chars. So in case there's nothing, we return a pure unit. Otherwise, we destructure the list to get like the head C and the rest C's. We use get to get our current state. And you can see here we're updating the state, or we're computing a new state. So if C is an ASCII letter, then, well, if it's a vowel, then we're going to increment the vowels. If it's a consonant, we're going to increment the consonants. If it's neither of those things, we're just not going to modify the state. Otherwise, we're going to throw a not a letter exception. Then we're going to update the state and loop with the rest of the characters. And obviously, it would be very easy in this case to just make the mistake of setting st instead of st prime, and stuff like that can lead to very difficult to diagnose bugs. And to like get around or like reduce the likelihood of such bugs and also actually improve the performance because we're not duplicating the reference, we can use this modify function, which, well, just lets us like directly modify the state. And in this case, the lean compiler should be smart enough to not actually generate a new state instance, but should see at runtime, okay, this is the only reference here, so it can actually modify it in place. And we are defining modify in terms of this modify get, which is part of the type class, where we can like both mutate and get the value in one step. And yeah, we can just modify get and just like return a unit instead of the actual state. Okay, let's look at the monad state type class. We have our state type sigma and our monad constructor, and yeah, the type of our class instance is going to be the maximum of u and v, like +1. Yeah, we have our get and our set and our modify get. I guess you could have like a default definition of modify get in terms of get and set. And p unit is a universe polymorphic type with only one element. So since we are writing this in such like a universe polymorphic style, I guess we cannot use a normal unit type. And okay, they're also writing here, yeah, we could provide a default implementation, but if we do that, then we have to like duplicate the reference, and that would make the optimization useless. So it would kind of make modify get useless. So I guess they're not providing a default implementation here. 6.2.4 of classes and the functions. So far, all of the type classes that we saw that have some extra information have that declared as an output parameter. And that's convenient because usually you have a single state type, environment type, and exception type. But if your monads grow in complexity, you might have multiple states and multiple error types. And in that case, it's impossible to target both states in the same do block. And for these cases, there are extra type classes that don't have the out param modifier, and they always use the word off in the name. So we have monad state off, which is like monad state, but without the out param modifier. And instead of out param, they are going to use semi out param. Okay, and semi out param also does not need to be known before Lean can search for the instance. Okay, well, this is a bit complex. The difference is, so the normal out params, they're just ignored in the instance search, and these semi out params, if we actually know the type of the parameter, then it can be used to narrow down the candidates just like a normal input parameter. I mean, so my understanding is right now of this, so if we think about how in the compiler a type class such as monad state is going to be represented, it's going to be some type of like hash map, basically, right? That goes from the input parameter, so from our monad constructor to our instance, right? So it's indexed by the input parameters, essentially. I mean, I don't know if they use a hash map or some other like structure, right? But we have this sort of state in the compiler that keeps track of all of our instances of our type class, such as monad state, and we can index into that data structure using the types, so the input types. So this out param is literally going to be ignored. So I think what that means is that literally we can have only one monad state instance for a particular monad type constructor. And obviously if this was like not an out param, then we could have a different monad state instance for each combination of M and sigma. But then I think it would be difficult or like annoying to specify which instance you want to use in your program at each point. Like you would need some sort of type annotation, I guess. And what I'm understanding now is that the semi-out param thingy will like allow us to have the best of both worlds, where if we know sigma, we're going to search using sigma and m for the instance, and if we don't know sigma, then we're just going to search for based on m, and I guess then it's gonna check if the result is ambiguous or not. So if there's more than one instance, it should probably still throw an error. Yeah, okay, it's also written here. When the state type is an out param, then each monad can have at most one type of state. And if we actually only need one type of state, then that's very convenient because that can improve our type inference. We don't need to provide type annotations. But obviously if you have multiple state t's in our like transformer stack, then we cannot get our monad state instance. Then we need to use this monad state off. And I mean, yeah, that will obviously work, but can then lead to confusing error messages if we're like accidentally accessing the wrong monad state instance. Yeah, then we get also accessor methods that allow us to explicitly specify the type of state that we want. So there's this getD method, which we need to like explicitly specify sigma, and same with modify the. And we don't need the set the method because the new type of the new state is gonna be enough to decide which monad transformer to use. And I mean, like always, when you have a more general thing, then you define the less general thing in terms of the more general thing. So the non-off versions of the classes are defined in terms of the off versions. So if you implement the off version, you are gonna get both for free, or like you're gonna get the other one for free. So we should generally implement the off version, but start writing our program using the non-off version and only transition to the off version if our constraint of like having the parameter as an output becomes inconvenient. 6.2.5 transformers and ID. So the ID monad is just the identity monad that has no effects, and we can use it in contexts where a monad is expected, but it's actually not necessary to use one. And we can also use it at the bottom of a stack of monad transformers. So if you do state T of sigma and ID, then basically you get something that is equivalent to just state of sigma. Exercises. 6.2.6.1 monad contract. Going to skip that, but basically it's to prove that we are satisfying the monad transformer contract here. Logging transformer. Okay, so we should define a transformer version of with log and also define a corresponding type class. Okay, so I'm going to just take like this type signature that they set as an example for what the monad transformer should look like. To our monad constructor, we have our like type of the actual data alpha, and we're going to return a monad that just contains a list of strings in addition to alpha itself. Then we need a monad instance. So given a monad M, let's see, we want to say that with log t M is also going to be a monad. Let's see what the AI does. Is obviously probably wrong. I think one thing we should maybe do is define these like make thingies. Let's see what did our AI do. So we get an X that is of type M of alpha and list of strings, and then we just give a with log t of M and alpha, and I'm going to try leaving out the universe constraints. Let's see if anything breaks. Then we need a run, which is going to be like the opposite. So it's going to be an X with log t M alpha and going to give us like the actual thing, just like the underlying monad with like a tuple as the type. And let's see if we can fix this by using our constructor. And indeed we can, and I guess it makes sense what it did here. So we have just an empty log in the pure case, and here actually we don't even apparently need to. Actually, that's right, it seems kind of nice to write. We're like running the action. Let's see, we run X, that gives us a particular log, then we run f of alpha, which gives us another log, and we return the result along with the logs appended to each other. Seems good enough for me. And what do we need? A monad lift instance. Okay, going to leave out the universe stuff, see if it works out. We have a monad M, we want monad lift. Is this the right direction? Yeah, we want to go from M of alpha to the transformed version, so M and with log. And let's see. So the way to lift an action into the logged context is to just like run it and return it with an empty log, right? I'm just wondering if we can make this simpler. So this doesn't work, right? Of course, we need to unwrap like the action. I guess that didn't make it any simpler. Okay, but anyway, let's try a type class. Let's see what was. So we need to probably take a monad type constructor and then use this universe generic unit thing. I don't know, but that seems about right. And then we want to make an instance like monad m for our like with log transformed version of the monad. And I mean, we're doing that by, wonder if we even need this. I guess we do. Yeah, by just like setting the actual result to unit and using like setting a single log message here. Okay, we should write a program that combines logging with exceptions. Just going to use this. I guess option T is close enough to exceptions. Going to write this abbreviation here to have log IO of user info. So let's try logging something, which doesn't work. Great. Maybe we need to like export. How does this work? No. Maybe I need to just like reorder these. Now it works. But what if we had them in the wrong order? So I guess this monad with log instance sort of expects the with log t to be like the outer layer somehow. And okay, let's write also a version of this. Do we need to lift it? So first of all, I wanted to log that we received an empty input, but then, well, how do I do this now? Why do I not get like the failure here? Because our option T has failure, right? What if I try this? Failed to synthesize. Alternative. Well, I wanted to use the make, not the run. So this works, right? But isn't this the reason we defined lift? I don't get it, but we can explicitly like do it by calling with log t. Let's try. So I'm trying to like define a run function that would allow me to like run this stuff, but I am failing. If I just run it twice, then well, I kind of lose the logs. So I can do a with log t dot run, right? And maybe the ordering was wrong in after all. So how I'm seeing it, the log should be outside of the option, but I guess we're storing the log inside of the monad that's passed in here. Alright, so I guess we need to reorder it. But then this stuff all fails because we are not, like it doesn't get lifted correctly, and I wonder why, even though I defined my monad lift. Do I need to define it in both directions? I guess. If I do that, then we're just deleting the log, right? And it doesn't even work anyway. Okay, now I somehow managed to get the log back, right? At least if I use with log t.run, then, well, we can see that we do get our log. But still, I don't like that I have to like manually lift this call to log message here. Well, so the AI can also not help me. So I guess I'm just officially too dumb for this. Anyway, okay, we should modify doc's monad using state t so that we can count the number of files and directories. So as a state, I guess we should, what maybe we should have the num files and num directories. If we add the counting state here, should be able to have, yeah, modify. Does this work? No, this does not work. So modify expects a function that goes from state to state, and apparently this is not good enough. Let's see. Why can we not just do like this? Because we need to access S, I guess. Okay, anyway. And I guess this would count them as like separate. How did they use it? Yeah, also the same way. Okay, now in main, if we restart, we should get an error. Okay, well, how do we get the state out is the question, I guess. Well, I mean, that's kind of ugly, but at least it works. And I think, yeah, just going to give up at this point trying to make this program nice. Well, anyway. 6.3 Ordering monad transformers. Yeah, so when we're composing together several monad transformers, the order in which we do that actually matters, because different orders will give us different monads. So we're defining here a version of count letters, like the previous version, but instead of providing a concrete monad, we just describe which effects we want. So obviously we want to have a monad instance, monad state for a letter count state, monad accept with error as the exception type. And I guess we're going to try combining the state and the accept monad in different orders. So M1 is state T of letter counts and then accept T inside, and the other monad M2 is the other way around with accept T on the outside. Okay, let's see. For M1 we get that accept T is like the outermost layer, and or like that the exception okay is like the outermost layer in the result, right? And M2 the state is the outermost layer and the state contains the exception, which is exactly the opposite order in which they appear in the definition. But I think this is because the way state T works is it stores its state inside of the provided monad, so it nests itself inside of the provided monad. So let's check what happens when we actually throw an exception. So if we use M1, where obviously the exception is on the outside, right? And we count the letters of hello with an exclamation mark. Yeah, we get an exception and we notably don't get a count. And if we use M2, then we get an exception, but we also get the state up to there. So we don't lose the state, because in M2, I mean, the accept T sort of nests itself inside of state T. So, I mean, depending on the use case, maybe M2 might be superior to M1 because you can still retrieve the count up to that point when the exception was thrown. So let's look at this count with fallback here, which tries to count the letters in the input string, and if that fails, it just counts the letters in the string fallback. And in the OK case, we get like the same counts for both of them. But in the failure case, well, now we're gonna get a totally wrong count, and actually with M1 we get only the letter count from fallback, and with M2 we get the combined letter count from fallback and from hello. So I guess because with M2 the state is kind of, I mean, here it's on the inside, but in terms of the data type, it's gonna be like the outermost constructor. So I guess the state is always preserved through exceptions. And I mean, that's kind of two really interesting behaviors, right? In M1, we roll back to the state where the exception was caught. In M2, the modifications persist and we can like carry on with the computation and like, yeah, just add to the vowel and consonant count. So M1 alpha unfolds to a function from letter counts to accept, error, alpha, and letter counts. So the letter count is nested inside of the accept, and in M2 obviously the letter count is like in a tuple along with the accept. Yeah, so in M2 an exception is always going to be accompanied by a state. 6.3.1 Commuting monads. So two monad transformers are set to commute if you can change the order without changing the meaning of the program. And so for example, state T and accept T do not commute because we saw that changing their order totally changes the meaning of the program. And obviously you cannot expect monad transformers to commute in general. If you have two uses, for example, of state t, then you can reorder them, because either you're going to have like this kind of structure where sigma becomes before sigma prime, or you're gonna have this kind of structure where sigma prime comes first, right? But you will still in the end need to provide the same inputs and get the same outputs. And in like a programming language that has in programming languages that have state and exceptions, like for example Python, it would usually behave like our M2 example. So the state persists even when an exception is thrown. And when you want to like roll back the state on exceptions, then you have to like manually implement that. And monad transformers give you the freedom, well, to choose an effect ordering that you want for your problem. And it's not going to like affect how easy it is to like write the actual code. But obviously, yeah, you need to take care how you order these things, because with great expressive power comes the responsibility to check that what's being expressed is what is intended. Yeah, and they're saying even themselves the type signature of count with fallback is probably more polymorphic than it should be. So it's not always good to like write the most general version, like especially if it's like an internal helper function, I would write like the concrete version that you need, so that, well, you know what you're doing, like not just in functional programming, but in everything that has generics, right? It's mainly useful for like stuff that actually needs to be used in multiple places and not for like a one-off helper function. Okay, so I think I'm gonna skip these because I'm already kind of tired. Maybe I will do them later, like without recording. 6.4, more do features. Yeah, Lean's do notation has this thing where you can write in like almost like imperative programming style, like more so than Haskell, because you can do like mutable variables and like, well, single branched if, as we will see, and for loops. 6.4.1, single branched if. Yeah, so something you might want to do is to have some side effect only if some condition is true. So for example, in this case, we had this else case here, which evaluates to pure unit, which just does nothing. And since this if is in a do block and not in the context of a normal expression, you can simply omit this branch and Lean will like insert it automatically. Yeah, so we can define it like this, where inside of the inner if we just don't have an else branch. Or we can write a program that uses the state monad to count the entries in a list that satisfy some condition. So we require that M implements monad and has a monad state instance with the natural numbers as the state. And we have this property of alpha that returns a boolean or boolean monadic action. And we get a list of alphas and we return a unit, and I guess as a side effect in the state we store how many x's to satisfy that predicate. Yeah, there's also an unless, which is basically just like if not you can use. And yeah, they just are going to replace the missing branch with like a pure unit. But then Lean can do some further transforms other than this, where it actually like inserts a local monad transformer. So one thing is 6.4.2 early return. So there's this list.find function in the standard library, and one way we could implement that is like this, where we just recurse through the list and, well, return some x when we found an x that satisfies the predicate. And in Lean there's also a return keyword that actually then can be used to like halt the execution. So if we look here, you can see we return x, and well, if this was Haskell, it would just like still execute this next thing, because in Haskell return is just like behaves the same as pure, but in Lean it's actually then properly doing what you would expect and like, yeah, stopping the execution here. And this early return is from the implementation. It's similar to an exception, right? And that's why Lean is also implementing it, just using in the except t monad transformer. And so it's just going to like essentially wrap your do block into a try catch and the try catch handler is just going to return the thrown value. So the type of the exception is just the same as the normal return type. So we can see here how this can be implemented. We have this function run catch, which takes a monad instance for a monad constructor M, and then an action, which is an accept T of alpha, M, and alpha. And we can see, well, the arrow type is the same as the return type. It just gives us an M of alpha. And it works by just running the action and checking if it is okay, then return. If it is an error, then also just return it. So if we look at what our list.find implementation would be translated into, it would be something like calling this doCatch, then starting a do block, and in our then branch just throwing our return value, and the else branch just well, putting a no op action. And another case where you might use that is if you have a CLI application that needs to terminate if the inputs are incorrect. So for example, we have this program here that just prints an error unless the argument list is empty, and then also uses early return. And if we just run it normally, it works, and if we give it an argument, then we get an error. Yeah, and if we did not use early return, then we would have to, like for example, introduce another level of nesting, which I think can make your code harder to read. Yeah, so the important distinction between Lean's early return and your normal, like, standard imperative programming languages return keyword is that in Lean it applies to the surrounding do block and not to the whole function, right? So this return here, this applies to the do block and not to the greet function. 6.4.3 loops. So obviously we don't, strictly speaking, need loops. We can just write them as recursive functions. And like depending on the context, it might be more clear to write something as a loop rather than as a recursive function. 6.4.3.1 looping with 4m. And Lean includes a type class that describes looping over a container type in some monad, and the class is called 4m, and it takes like a monad type constructor and a type gamma and a type alpha, which is marked as an out param, and has just one method for m, which takes some type gamma and some function that produces an action based on a type alpha, and then it returns like an action that returns nothing, I guess. So gamma is supposed to be the collection type, and alpha is the type of elements from the collection. And usually M is allowed to be any monad, but there's also cases or data structures that only support looping inside of the IO monad. And yeah, 4m is just going to run the action for each element in the collection. So here we can see how we could implement this for list. So we have list.4m, which takes a list alpha and again some consumer of alphas. I guess that is an action for each element. And yeah, in the end it's just implemented using recursion, just running the action and then recursing to the rest of the elements. And in our dog example from the previous chapter, yeah, we had this do list helper, which is just like 4m, but specifically for lists. And I mean, it's supposed to be used in do blocks, so we're using the monad type class here instead of applicative. And if we use 4m, we can make our count letters function much shorter. So we can just call 4m and then pass the list and the function of what to do with each element. We can also implement a 4m instance for many. I think many was just like a lazy list, right? We run the action on the first element and then we like evaluate the rest of the list and run the action for that. And because the type of gamma is not constrained, 4m can also support non-polymorphic collections. For example, we can make one that contains all natural numbers less than a given number, where we just store our like upper bound and have this like countdown recursive function that's just going to call the action n times with n as an argument. I guess we're starting from the biggest number here. And yeah, like with like this, for example, we could just print all numbers that are less than 5. And there's also an example of something that only works in one particular monad. For example, if we want to loop over the lines of some stream, We can define a partial function for that. I guess that condition for ending the loop is if there's an empty line. Otherwise, we like run the action and call ourselves recursively. And obviously, we have to mark it partial because the stream could be infinite. And here we have an example program that uses this looping to filter out lines that don't contain letters. So we call the constructor of lines off with the stdin file descriptor. Then for each line, we check if there's any alphabetical character, and if so, we print the line. 6.4.3.2 stopping iteration. If you just use this 4m, then it would be hard to like terminate the loop early, because you don't really have a way to just stop the loop. And we can, for example, simulate this using the option t transformer. If we define a function option t.exec, which takes an applicative m and an action of type option t m alpha, and then returns a m of unit. So it's just going to discard the return value and then return pure. But I guess if the action returns none, then somehow we will be able to short circuit. If we have numbers all less than n, we call option t.exec, and for each number, if it is less than 3, then we return an alternative .failure. And since this is such a common thing to do, Lean provides a syntactic sugar for it, which is just like the break keyword, basically. And this for in do syntax that we see here, that desugars to the type class for in, which is a bit more complex than for m, because it keeps track of the state and of early termination. And we don't actually need to define for in instances, because there's an adapter that converts a for m instance into a for in instance. Yeah, and inside of for loops we can also make use of the early return. So like in this example, which is another way to write list.find, loop through the elements. If there's one that satisfies the predicate, we return it. And yeah, I mean, you can see we have two do blocks here, so actually you could think it replies to the inner one, but the documentation here says uses of the do keyword in other syntax like for in do not constitute a surrounding do block in this sense. So yeah, it's actually short-circuiting from this outer return. And continue is also supported, so you could also write it like this. So in Lean there's std.range, which is a structure that has a starting and an ending number and a step. And there's a special syntax for ranges using square brackets that actually reminds me of like the syntax that's used in Python. And the only thing that you have to provide is the stopping point, so you can leave out the start. So if you write it like this, it's numbers from 0 to 9. So the end is exclusive, I guess the same as in Python, like list slices or whatever the feature is called in Python. Yeah, you can also provide like a step. I wonder if we can, I guess they have to be natural numbers. I can't like do a negative step, because in Python, right, you can do this, like you can do from index 50 to index 42 in steps of -1, but I guess they have to be natural numbers here. Yeah, also what they're saying here, we cannot count down in a range. And if the starting number is greater than or equal to the stopping number, then the range is simply empty. And we can use these ranges in for loops. So we can do like for I in from 4 up to 9 in steps of 2, print I. And the for syntax also supports like iterating over multiple collections in parallel. So I guess like the zip function in other languages. And there's also some data structures that provide evidence that the element was drawn for the loop body, and you can use this sort of syntax to access that evidence. And that evidence can, for example, be used to prove that the array lookup is safe. So for xs at I, since we have this evidence h that we drew the I from this range, I guess we can deduce that it's safe to use I as an index into xs. 6.4.4 mutable variables. So in addition to the other like imperative features that we saw, we can also have mutable variables within a do block, and it's going to desugar to a state t instance. And like in Rust, we can introduce them using let mute. So we can do something like this, where we just have an X and modify it, which internally is just going to be turned into this, right, into a state T and calls to modify. And I mean, obviously we can like combine mutable variables with for loops. And actually here you can see that we are just using the ID monad like to get a do block. There's otherwise no need why this code needs to be monadic just to get the syntactic sugar. Yeah, we can also like have a count function where we count how many elements in the list satisfy a predicate just in normal imperative style. And obviously Lean being a functional language, I mean, these aren't like fully mutable variables. They can only be modified in the do block that introduced them. So you cannot like replace a for loop with a recursive helper function like this. So because here we are in a different do block, right? So we cannot like modify this other value from the other do block. 6.4.5. What counts as a do block? So we now saw that many features only work within like one do block, like early return and stuff like that. And to know how to use them correctly, we need to know what counts as the same do block. So in this case, we have one do and everything at the same indentation levels. Obviously, this is one do block, right? And here we introduce another do and another indentation level. So then that counts as a separate do block. But there's some like special cases. So here we are obviously using like the normal assignment syntax, and then it is a separate do block. But if we use the like bind operator, right, then it becomes part of the same do block. Like this arrow obviously is going to be desugared into a bind, a monadic bind. Yeah, so if we call a function and pass it a do block, then that also counts as a separate do block. If the do keyword is completely redundant, then it also doesn't introduce a new do block. So if you just randomly write do here. Yeah, I mean, I think this is pretty easy to understand if we just like think back to the desugaring rules for do blocks. You have to just, well, like think about what sequence of bind operations it gets like translated into. The branches of match and if are considered to be part of the same do block, so this works. Even if we add like a redundant do here, it still works. Same with the matches here, even if we add another do. And the do that occurs as part of for and unless, that's just part of their syntax and it's not actually a do block. So I guess they chose a pretty confusing keyword there for that syntax, since this do then is not really the same as that do on the top. And same here. 6.4.6 Imperative or functional programming. Yeah, obviously with these imperative do blocks you can write code that looks almost like Rust or Java or C#. And for some tasks it's just easier to accomplish them using this like imperative style. And we sort of get the best of both worlds because we still get like the strong reasoning principles and like the immutability, the tight control over effects, but we also get like the readability that comes with like the familiar imperative syntax. And I mean, you always have to remember like these mutable variables, they are like constrained to that do block, so they're like a local thing that you could also like refactor away with a simple translation of the code into like the desugared, like purely functional state T code, right? So it's just like syntactic sugar for that. It's not like really mutability in the same way that imperative languages have it. So yeah, it's just like a matter of preference or perspective, I guess. Rewrite though to use for instead of to list. I already did that. I think I already used some other in some other places I already used like let mute and like the single branch if and stuff like that. 6.5 Additional conveniences. 6.5.1 Pipe operators. In some programs it's useful to write them sort of as pipelines. For these, Lean provides this pipeline operator, which I guess is just like function composition, right? Or function application actually, because it's maybe more natural to read like first we turn it into an option and then we convert it to a string. rather than writing toString dollar $sum5, which would be like the usual way to write it. And yeah, I mean, the more transformations you do, the easier it can make stuff to read. So if you read this, like start with 5, multiply it by 3, turn it into a string, and then prepend it is, and then you get it 15. So otherwise, either you need like a lot of dollar signs or you need a lot of parentheses. And there's also like a reverse pipeline operator that goes in the other direction. Obviously, in that case, you could also just like write it using parentheses, but it'd be clearer to use that operator. But like the thing is, I mean, let's look at, like we could just as well have written this using the dollar operator, which I guess even here it says it's just an alternative syntax for this operator. I wonder if like the precedence and everything is actually the same. But yeah, I mean, obviously also you could write it using, how do you write that? Function composition. So yeah, you can also write it using function composition in that case, with dollar. Yeah, sometimes I just think that functional programming languages have too many operators, especially too many similar ones. Anyway. Yeah, and in Lean obviously there's also just a dot operator that is similar to pipelines. If we like define it like this, I think then we could do, okay, not does not have a toString, but anyway we could like call it like this, right? Can also work similarly to a pipeline. Yeah, but the pipeline can still be clearer. So if you have this 1, 2, 3 dot reverse dot drop dot reverse, we could write it like 1, 2, 3 piped into reverse, piped into drop 1, piped into reverse again. And yeah, then we get a similar convenience to like a chain of method calls. But in that case, we need to like provide the namespace manually, like list. So there's another convenience operator, which is pipeline dot, that uses the name of the type to resolve the namespace. So then we can rewrite it like literally just like this. Yeah, which doesn't look weird at all. 6.5.2 infinite loops. So we can use the repeat keyword to introduce an infinite loop. If we just want to keep printing spam, we can do it like this. And they also support break and continue, just like for loops. So in this dump function here, we just use recursion to loop forever, but we could do the same using the repeat keyword. And one interesting thing here is that partiality does not infect the calling function. So this dump function is not partial because repeat makes use of a type and the 4m instance of that type is partial. Yeah, so partiality does not infect calling functions, but honestly not very surprising in this case, I think, because it just returns an IO of unit, which you can think of as like a value, right? So it does return, just returns this value that describes this computation, but it doesn't actually run it, right? Just constructs it. And you can run it by passing it to an eval, to a hashtag eval, or like assigning it to the main action, right? 6.5.3 while loops. Yeah, I mean, in addition to repeat and for, we also have while loops. I think nothing too special about that. So while is just implemented in terms of repeat in the background. 6.6 summary. 6.6.1 combining monads. So there's all these design patterns for adding effects to your monad, right? You can add a reader effect by having the monads type be a function from the environment, and I mean the state effects you can have by making like a function from the initial state and pairing the value with final state and so on. And we can make a library of reusable software components from these sort of design patterns by defining monad transformers. And monad transformers take a simpler monad as an argument and return the enhanced monad type. And usually a monad transformer should provide at least a monad instance and a monad lift instance. And you can implement a monad transformer like as a polymorphic structure or as an inductive data type, but the most common thing is to just implement them as functions from the underlying monad type to the enhanced monad type. 6.6.2 type classes for effects. And another design pattern is that if you want to implement a particular effect, you define a monad for the effect, you define a monad transformer that adds it to another monad, and you define a type class that provides a generic interface to that effect, and that allows programs to be written in a very general way, where they only specify which effects they need, and the caller can then provide any monad that implements those effects. And yeah, for these type classes, sometimes you want auxiliary type information as an output parameter, and sometimes not. Really depends on if you want to have like multiple instances in the set of that transformer in your stack, or if you really only like need one of them. And usually you provide both versions for flexibility, and yeah, you use a type class that ends in off for the like non-output parameter version. 6.6.3 monad transformers don't commute. Yeah, so if you have stuff like state T and accept T, the order in which you apply them obviously makes a difference. And this is a sort of decision that imperative languages make for you. So obviously you can use state and accept in imperative languages, but how they interact is something that the designer of the language decided. Whereas like in Lean, you get the flexibility to have like both behaviors depending just on how you order the effects. 6.6.4 do notation for monad transformers. So Lean's do notation is super useful. It has some like convenience imperative programming features. Obviously that's not really imperative programming, it's just a syntactic sugar for some common monad transformers. But yeah, nonetheless very useful. By the way, if you want to see like a different take on effects, I think you should totally check out like effect-based programming languages. For example, Coca, I think is a really like interesting one. Like there doesn't seem to be any like real production use of this type of language yet, but like as a research area, I think it's very interesting because they seem to provide like a lot of the same benefits of like monads and monad transformers, that you can clearly control your effects and like have pure functional code as well as having I/O, and that you can also like combine different sorts of effects. But I think like cognitively, it's so much simpler to think about. Like literally just write the effects in the type signature. Like if you want to print to the console, you write console. If you want to throw exceptions, you write exn, and then you write like the return type, right? Well, I don't know why it doesn't seem to be used in any like production ready languages, but I think it's actually pretty interesting alternative to monads to check out at least. Okay, yeah, with that being said, see you next time where we look at programming with dependent types.